we've seen how to find the first derivative of these, or the first partial derivative, excuse me, of our functions. So let's take a look now and be able to find second partials of functions. And let's see if there's some sort of relationship between some of the second partials. So fxx. So to be able to find fxx, we're just going to start by taking the first derivative. So fx is going to be equal to derivative of cosine is negative sine. We keep the interior function as xy, and then the derivative of xy with respect to x is going to give us a y. Derivative of x cubed y with respect to x, 3x squared y cubed. Now fxx, fortunately, is not too bad for us. So derivative with respect to of sine is going to be negative cosine. And then we still have the derivative of the interior function. The derivative of the interior xy with respect to x is going to be another y. So we have y times y. All right, so this y just kind of dropped down. All right, as again, think of it like a 5 or a 7 or something like that. Derivative of 3x squared, 6x, and then the y cubed just comes down. Right? If we wanted to factor out a y square, we certainly could. So another way to write this, y squared quantity, 6xy minus cos xy. And that might be the nicest version that we can get. Now let's see if fyy is any different. Okay, so fy, first of all, derivative of our cos xy is again negative sine xy. Derivative of xy with respect to y is x. Derivative of x cubed y cubed is going to be 3x cubed y squared. And fortunately, fyy is not too bad. Fyy, derivative of negative sine is negative cos xy. We still get another x for that interior function's derivative, and then we're just going to drop down the x that was initially there. All right, so we'll get an x squared, and then derivative of 3x cubed y squared, 6x cubed y. Just like we did before, we can factor out an x squared instead of a y squared, and we will be left with 6xy minus cos of xy. All right, and notice that the two functions are very, very similar, but they are not the same. In general, as a general rule, fxx is not equal to fyy in general. Now there are a few functions where that is true. Like for instance, what if we had 3? All right, well, that just makes sense. If we had the plane z equals 3, then the slope is going to be 0 in both directions, and then the rate of change of the slope, or the acceleration, would be 0 as well. So there are times to where fxx is equal to fyy, but they're very trivial cases generally. Now what about these types of mixed partials, fxy and fyx? Now let's go back up here, and remember we have cos xy and then x cubed y cubed. So remember our function is cos xy plus x cubed y cubed is our function f. So let's start with fx, which we already have. All right, so remember we go up here, and fx is going to be negative sine xy times y plus 3x squared y cubed. Now we're going to find fxy, and unfortunately fxy is a product rule for the first term. All right, so derivative of sine, negative cosine, and then the derivative of the interior function with respect to y this time is going to be x. So we have xy, and then we're just going to go ahead and take the derivative of this y, so we're going to have minus sine xy. All right, so this is our product rule. And then the derivative of 3x squared y cubed with respect to y, 9x squared y squared. All right, so let's hold on to that solution. And now let's find fyx. And the good thing about fyx is that we already have fy. All right, so we go right here. Remember we had negative sine xyx, 3x squared y squared. So fy is negative sine xy times x plus 3x cubed y squared. All right. Now we want to find fyx. And similar to the previous, we are going to have to use a product rule once again. Derivative of sine is negative cosine. The derivative of the interior function with respect to x is y. And then we just drop down this x. And then we're going to go ahead and just take the derivative of the x, which is 1. So we have a minus sine xy. Derivative of 3x cubed y squared with respect to x, 9x squared y squared. Now, let's take a look. Same. Okay, just the y and the x are reversed, which is perfectly fine. We have negative sine xy, we have negative sine xy, and then finally, we also have this 9x squared y squared. So did we get lucky? Or in general, is fxy equal to fyx? So is fxy equal to fxy? And the answer to that is yes. In general, it is. And that's actually Clairaut's theorem. Clairaut's theorem says that if f is continuous on a disk and contains a point AB, the second partials fxy and fyx are indeed equal to one another. All right, so, and we just look at that, what we just had above. Clearly it illustrates it for a singular example. All right, now that doesn't mean that it proves it, but at least it reinforces it. One last thing before we go through and start taking a look at partial differential equations and verifying them is just to understand what fx and fy represent. And fx and fy represent the slope in the x direction and the slope in the y direction. So as you can see here, I have an example to where we go through, we find the partial, and then we substitute a value in at that point. And that tells us what the slope is exactly at that point would be in the direction of x. And you can see from our diagram, essentially we're going to have like almost a tangent line at that point in the x direction and a tangent line in the y direction. All right, so essentially, once again, fx and fy just tell us the rate of change in a specific direction. In the last video for this section, we're just going to take a look at what we do to be able to verify partial differential equations.